eighth graders. I'm so glad we are able to give you guys a presentation this year. We're going to show you some really cool visualizations on a tool that we invented. My name is Hilary, and my colleague here is Beth, and we're kind of tag teaming here on this presentation. Normally, we would be showing you this on a 6-foot sphere in a theater. Luckily, because of current circumstances, we have also put most of those data sets right on a flat screen device. So we're going to look at some real-time events that have been happening, like Hurricane Laura, and check out the fires. And then we're going to go into some topics that you typically study in like an 8th grade earth science class. And finally, we're going to tell you how you can see pretty much all these data sets on your own personal phone as well. So let's hop into it. First, we're going to start with our blue marble and nighttime lights data set.
And so every data set we show you, we're going to be asking you questions for you to think about, answer to yourself or to whoever's sitting with you. So as we're looking at this data set, can you pick out the different types of data that are layered in this image? What do you see that's included here? So there's a couple different things here. So as Hilary's zooming in and browsing for us, take a look. Since I sadly cannot hear your answers, we're going to have to share our answers for you. So Hilary, what types of data do you see?
Yeah, so normally when you would look at the Earth, depending on what kind of satellite it was, you wouldn't see all of these things. If you were an astronaut in space, for example, you would in fact see the day side of Earth and the night side of Earth. So you would see, if you were on a satellite that was close enough to Earth, you might be able to see these nighttime lights, which is a little hard to see, but hopefully it's coming through there. And you would also see the clouds, so that's really great. But probably, Beth, what would you not see from space?
So you wouldn't see the ocean shaded the way it is. So right now the ocean is colored so that you can see the seafloor. So those lighter blue areas around Florida, that's where it's not quite as deep. And then those darker areas represent deeper areas. Or Hilary, if you swing over to the Atlantic Ocean, through the middle, what we can see is this line cutting through. That is the Mid-Atlantic Ocean Ridge. So from space, you would not be able to see that. The ocean would look just like a dark surface. You might see some coloring like around the Caribbean islands where you get those nice teal beaches that can show up from space. So that's something that you wouldn't be able to see.
Yeah, so satellites work differently than our eyes in the way we see things. And so these are all different data sets that are collected from all kinds of different satellites and then overlaid onto this one beautiful image.
So this is giving us
a handful of the 1,100 active satellites zooming around the Earth as we speak.
Yeah, and these satellites are doing all sorts of things. So we were just talking about how they measure clouds for us. We can use them to detect those nighttime lights. We will show you we can use it to look at sea surface temperatures, sea ice concentration. And there's different types of satellites. You'll notice there's some very close to the Earth, circling around the poles. Those are called polar orbiting satellites. And then there's this ring further out, actually 22,000 miles out from the Earth's surface. And those are called geostationary satellites. And you'll notice as the Earth rotates, they rotate with it. So they're always above the same location so that we can get continual coverage of certain areas. So like over the United States, we have 2 different NOAA satellites that are positioned out in geostationary orbit that are continually monitoring. So you can see ours are called GOES, Geostationary Operational Environmental Satellites, and we number them. So we've got GOES 14, 15, 16, and 17. 2 are operational and 2 are backups in case anything goes wrong with the first 2. So those are our satellites. So why don't we jump to our next data set and take a look at what we can do with satellites. So that first image we were looking at showed the clouds, but it was just a static image of the clouds. So now we're going to look at the clouds over the last month. And if you've been paying attention to the news at all, it's been an interesting month in the weather world. So my question for you here is, what patterns do you see in the clouds, and what does this motion tell us about the atmosphere? So Hilary, you're going to have to be my stand-in student. What do you see?
Yeah, I'm just giving a little bit of time in there so that folks can hear themselves think. But yeah, so it looks to me like the clouds are moving in lots of different directions. Right along the equator, you can see that they're kind of moving from east to west. Up where we live, I'm going to pause it there. Up where we live, they tend to move from, I'm going to back up just a little bit so we don't miss that, but they kind of tend to move from the Pacific, and then they're always kind of waving or spinning.
Yeah.
So I think this says that the atmosphere really moves in different directions depending on where you are on the planet. And then if you dig a little deeper, weather can be has certain patterns to it.
Yeah, absolutely. And you have paused on a great frame, because here we can see Hurricane Laura. And we heard in the news Hurricane Laura was a very powerful hurricane. And this image here shows us why. So when a hurricane is really symmetrical, when it has that nice circular shape with a very clear eye, that means it's super well organized, and that allows it to really get strong. So Hurricane Laura, if you back up just a little bit, a few days before this, we didn't realize that Laura was going to be such a powerful storm, but it intensified very quickly. It came into the Gulf where there were warm waters, and it very quickly, look at this point, there's a storm there, but it doesn't necessarily look like too much, but it really exploded into a massive storm right here. As you see that eye up here, it was getting very strong very quickly.
That was a rapid intensification. That's got to be a little bit scary.
Yeah, absolutely. So that's one look of something in the atmosphere that we can see, the clouds. That's the obvious one. So let's take a look at something we can't see with our eyes, but satellites are able to detect. So here we're looking at ozone concentration, and I'm sure you've probably heard of the ozone hole. So my question for you is, where does it occur? So look at the color bar. Anything under 220 Dobson units is considered an ozone hole. So watch the loop and see where the hole forms.
Yeah, so if you're good at geography, you might notice that this is the Antarctic continent. So it's happening over the South Pole, essentially, kind of moving around the South Pole itself. Beth, it looks like we really didn't have a big hole last year. That's pretty interesting, huh?
I do think
was last year the year where we
it didn't get cold enough, I believe, for the ozone hole to really open up as much as we're used to. So I do believe last year was a lower year. So there's a couple things you need for the ozone hole to form, and one of those is really cold temperatures. So when we don't get quite cold enough, we don't see it open up as much. So that's a good thing, but also a bad thing because it means our planet is not what it used to be. It's changing. The main thing that we need for the ozone hole are I'm blanking on the name. The fluorocarbons.
CFC?
Yes, sorry. There you go, guys. My goodness. The CFCs, chlorofluorocarbons. So it's from refrigerants. It's been banned now. It was banned in the 90s before any of you all were born. There's still a little bit of it in the atmosphere though. So this chemical, when it combines with really cold temperatures, destroys ozone.
Yeah, so one of the reasons it has to be very cold is because two other pieces are needed to break apart this ozone molecule. And ozone is O3, so it's three O oxygen molecules, oxygen atoms. You need sunlight, so that's why it happens in the spring. Notice the date. The spring in the southern hemisphere is opposite than it is in the northern hemisphere. So you need sunlight to come in and break the bonds, and you also need ice crystals in the stratosphere. And if it's not cold enough, then you don't have the ice crystals, which act as like a cutting board for the sunlight to come in and break the bonds. So yeah, that's an interesting side effect of climate change, that we don't have as big of an ozone hole. And when you hear about ozone in the news, like for example, this summer, Boulder has been some of the worst ozone concentrations ever reported in Boulder because of the fires and hot temperatures. But that kind of ozone is pollution right here in the troposphere, which is where we live. This is the stratosphere that we're looking at. So one layer above, which is really, you can denote this layer by looking at airplanes, like I'm looking at an airplane right now, and see how high it's flying and think, okay, above that airplane is the stratosphere. And ozone is actually useful for us in the stratosphere because it acts as a sunscreen.
Yes, without ozone, we would all be getting sunburns. I get sunburns anytime, anyway. But ozone helps protect and not get quite as many. So we got to keep moving along. We've looked at the atmosphere. We're now going to move to the hydrosphere. So this is looking at the water on our planet. And what we're looking at right now are sea surface currents that have been colorized based on the temperature. So if you look at the color bar, it's in Celsius. So 0 is freezing. And then it goes all the way up to 32, which is in the 90s. So that's pretty toasty. So take a look at this and try and think about, why are sea surface currents so important for Earth's climate?
Yeah, so I decided to put the countries on this map during this data set because I wanted to kind of draw your attention to the fact that there's actually quite a few people living at pretty high latitude. So if you take a look at the Arctic Circle and then you go kind of one line down from there, we're looking at places that traditionally don't get a whole lot of sunlight year round. The angle is really sharp. They're just not getting too warm. Places like Finland, Norway, Sweden, Ireland, United Kingdom,
Alaska.
Iceland, Alaska. Absolutely. So these are places that, in all honesty, without these sea surface currents, probably wouldn't have people living there.
And how, what's the impact that why do sea surface currents make a difference?
Yeah, so if we try to follow this particular hot water from Africa, where we know things were really hot here at the equator, and we've had to follow it up the continental, up the two continents here of the Americas, and then we kind of see it curving over across the North Atlantic. You can kind of see that the North Atlantic is kind of green as opposed to blue. So the idea is that these currents are essentially bringing warm water where there's a lot of heat up along the coast and to places where there's not. And warm water basically reacts with the atmosphere above it and causes the atmosphere to be warmer. So if you look at the difference between the green currents by Norway and the blue currents by Greenland, you know, these are at the same latitude, but because of this particular current and the way that it flows, it's really keeping these areas in Scandinavia a lot more temperate and a lot warmer than, for example, Greenland. Does that make sense?
Yeah, absolutely. So warm water helps warm the atmosphere, and certain currents are moving that warm water northward. So like if we look at Japan, we can see the same thing where warm currents are moving along the equator and then making their way northward, and then also southward, like along Australia. But those areas that have that current bringing that warmer water towards the poles are going to be places that are going to be a little more comfortable to live. So those are our ocean currents. Now, it's hard to identify which areas are hot. I mean, we can see hot and cold, but we can't tell if they're hotter or colder than normal. So what Hilary has loaded up here for us are sea surface temperature anomalies. So again, always look at the color bar. We're looking at sea surface temperatures compared to the 1981 to 2010 average. So we always take 30 years to call it average. And so areas that are red are warmer than that 30-year average. Areas that are blue are cooler than that 30-year average. So why would we use an anomaly map in climatology?
Yeah, so just like what Beth said, when you see these red lines and blue lines, you can have a sense for how they compare to each other. So how the water near Norway compares to the water near Africa. But it doesn't give you a sense for how is that changing over time? Is it colder than last year? And this is really important. So if you have ever heard, for example, we think it's going to be a wet winter, or we expect fires this year to be bad, or something like that. Really, if we're trying to predict 3 months in the future or 6 months in the future, one of the only tools we have are the temperatures of the ocean. And one of the most important of those is for us here in North America is El Nino. And so this area right here that I'm kind of zooming in on, this huge swath of the South Pacific, right in the middle of the Pacific, more or less, is, if it's colder than normal, like it's showing here, it's showing in a La Nina pattern. If it's warmer than normal, so you see a big swath of red, that shows more of an El Nino pattern. And these affect our climate quite a lot, especially in California, where they're heavily dependent on El Nino for a little bit wetter conditions.
Right, exactly. So knowing temperatures of the ocean in one part of the world impacts the general weather in another part of the world. Our whole Earth system is interconnected, and that's one of the great ones to show that difference. So I'm going to jump to our next data set. We've looked at ocean temperatures and the water in the oceans. Let's look now at the frozen parts of our ocean. So what Hilary's going to pull up for us is sea ice conditions, but we're only going to look at September. So my question for you is, well, I have two actually. The first is, why would we be interested in looking at only Septembers? So we start in 1987, go up till last September, but only Septembers. So why would we look at only September? And then also, Hilary will have to do a little work for us here. What are the similarities and differences between the Arctic and the Antarctic?
Yeah, so September, what you're seeing here is really very small sea ice concentrations. And that's because Arctic sea ice concentrations, so the North Pole. And the reason for that is we're only looking at September because it's at the end of the warmest season of the year. It's really the furthest melted, the least amount of sea ice. We call it the minimum sea ice concentration. So September is really important because what we're most worried about is the Arctic sea ice, not just because a lot of people live in the northern hemisphere, but because it's faring a lot worse than the Antarctic sea ice. And so we look at September to be able to compare year to year. And so we can kind of see a pretty big difference between 2000, let's see, I believe 2018 was the last one we had here. And if I zoom back to 1987. So on a globe, it might not look that much different, but that's a huge amount of area. And this year, I think we are going to see, and I really suggest that you all go and look at the sea ice concentrations this year. Maybe go to the National Snow and Ice Data Center, because I really want you to see what's going on in sea ice concentrations this year, because it's shaping up to be another minimum record.
Yeah. Now, so you answered our September question. What about the difference between the poles? So if you look at this pole, notice there's a lot of land and ice in the middle, and the South Pole is the opposite.
Yeah, and I think that's a fairly large reason why the South Pole is faring better. Not to mention it doesn't have a lot of land around it, so it stays pretty cold all the time. But yeah, first of all, September is the sea ice maximum for the southern hemisphere. So this is like the biggest that it gets throughout the year. And then also you have this huge continent that's right in the middle that's kind of keeping a lot of cold and ice and lack of people living there as well.
Yeah, it's isolated.
Go ahead.
Absolutely. So that is a look at our sea ice. We've got to keep trucking along here. So let's jump to the tsunami.
Mm-hmm.
So we are going to look at a tsunami that happened in 1700. And we weren't recording earthquake strengths in 1700, but through people recording that trees had fallen over, that they felt an earthquake, we were able to figure out that a tsunami happened off the coast of North America, but the wave was so big there were impacts felt in Japan. And originally the people in Japan were super confused about what happened because they didn't feel an earthquake. And scientists years later have put together that these two events were related. So the question that we have is, why would we model past tsunamis to help us prepare for future ones?
Yeah, so what we're looking at here is actually called the Rift model. and I forget what it stands for. That's how he remembers. But it's a model that looks at earthquakes, and it's consistently running. So if a huge earthquake happens right now, this model would run, give us a sense for how fast the wave is moving, where the wave is going. The tsunami warning center in the Pacific or in the Atlantic would send out basically a warning to folks who live along the coasts, um, and it would make its way to other countries. So the idea is that if we take the details of past tsunamis that we know and we input them into this model and we see what happened, that gives us a better gauge or something to measure from for current tsunamis that are happening, or ones that happen in the future.
Right. So we can look at what's happened previously and assume future ones will act in similar ways. So it helps us better prepare. So I'm going to have us jump to our last data set because we are out of time with you guys. We've just been having so much fun. We can talk about this stuff forever, but we're not going to make you watch us forever. So we have jumped to our last one, and I'm not going to tell, well, it's labeled on here. Read your labels and you'll know what this is. But what comes to mind when you first see this data set?
Yeah, some of the words that folks have said in the past when I've asked them that question have been ants or busy or globalized. Um, Basically, airplanes are flying a lot all the time, and it's important that we're understanding that situations like the present where air traffic has slowed down a dramatic amount, has really changed some of the pollution in the atmosphere. So different types of nitrous oxide, or nitrogen dioxide, sorry, and other kinds of pollution. Beth, what other ones besides nitrogen dioxide have gone down, have been reported to have gone down dramatically?
I mean, that's the big one that's been reported on a lot. I think any of the pollutants, right? So your black carbon aerosols and sulfates, all of the things that people create, particularly through transportation, we're going to see a drop, or we have seen a drop in those due to the lack of travel and people staying home.
So our impact on the planet is pretty dramatic, and when we all stay home, our impact really lessens. So although COVID has been a really unfortunate and horrible situation, it has shown some impacts in a good way on our atmosphere. And it's interesting to look at data sets like this and just kind of see, wow. I think I calculated at one point that in a 11-hour flight on a 280, or trying to remember the type of airplane that I did the math on, but essentially 384,000 pounds of carbon dioxide goes into the atmosphere from one flight. So our impact is great, and that's why we have to figure out how not to use certain types of fuel so that we're not emitting so much carbon dioxide into the atmosphere while we're continuing to have this pretty amazing globalized, super fun and interesting economy and life.
Yeah, and that's part of why we do 8th grade Science Day, to inspire you all to become scientists so that you can help us figure out what that new fuel is and ways to keep moving forward so that society can continue to progress, but in a way that is kinder to our planet. And unfortunately, we are now at the end. We have run over our time, so we just want to wrap up real quick and thank you for joining us today. If you've enjoyed what we've been looking at, we are using a program called SOS Explorer, and there is a version that you can run on your phones. So look in the app stores, both Apple and Android have it, and you can look at most of these same data sets right on your phone. So be sure to take a look. And thank you so much for joining us today.
Thank you so much.